Welcome to our next Math 2110 video. In today's video, we're going to talk about the division algorithm and modular equivalence. So the division algorithm is just an algorithm that describes the long division that you learned probably in elementary school. It says that if we have a number and we divide by b, a positive number, b will go into a some whole number of times, which we call q. Q is a whole number of times that b goes into a, and then there'll be some remainder r. And since r is the remainder, it has to be smaller than b, and it can't be negative. So if we illustrate this, we could write 13 equals 4 times 3 plus 1. So we'd call that 1 the remainder, and so he's our r, and he's positive, and he's less than 4 that we were dividing by. The 3 is the quotient, the number of whole number of times it goes in, so it's q. The 4 is the divisor. He was given to us, and he has to be positive. And then we might call the 13 the dividend, what we're dividing into. And the division algorithm says that it goes some whole number of times q, and that then there's a remainder, and the remainder has to be non-negative. So the divisor must be positive, and the remainder has to be non-negative, so the remainder must be non-negative. And that's important. So it has to be greater than or equal to 0, and it has to be smaller than b, what we were dividing by, because otherwise it would have gone one whole more time. It's just formalizing the division that you're used to in elementary school, and just like it was in elementary school, right, there was a right answer. There's one q that works and one r that works. Those integers q and r are unique. So if we now think about in this example, we're going to apply the division algorithm using the dividend a, so we're dividing into a, and what we're dividing by, b, is given by b. So we have 13 and we're dividing it by 3. So 13 is 3 times 4, that gives us 12, and so we have a remainder of 1. So this is the division algorithm expression of dividing 13 by 3. 3 goes into 13 4 whole times with a remainder of 1. So that 4, the number of whole times, is called the quotient, and the 1, what was left over, is called the remainder. Now let's try it with negative 23. If you remember from the previous slide, the remainder has to be positive. So we're not as used to dividing into negative numbers from elementary school, so you have to think a little bit about this one. But I'm going to have to add a positive number to a multiple of 4 in order to get negative 23. So I'm going to need to overshoot negative 23. I'm going to have to be more negative than negative 23. Then I can add something to get back to negative 23. So I'll take 4 and multiply it by negative 6. And so 4 times negative 6 would give me negative 24. And then I can add 1 to that to get to negative 23. So again, we have a remainder of 1. But this time our quotient was negative 6. So that might be the part that's the newest in this case, was the second example. And so we had negative 23, and we wanted to multiply 4 by something and then add something to get to negative 23. So we had to overshoot. We had to be more negative than negative 23. So we chose 4 times negative 6 because that gives us negative 24. And then we can add back 1 to get to negative 23. So next we're going to talk about modular equivalence, which might not at first seem equivalent to the division algorithm, or related to the division algorithm. It's not equivalent, but related to the division algorithm. But we'll see soon why it is related to the division algorithm. But first let's get comfortable with the definition. So if we have two integers, a and b, and n is a natural number, so positive, we say that a is equivalent to b modulo n, and write this, a with the 3 bars, b, parentheses mod n. What that means is that n divides a minus b. So if we had something like 13, we could say 13 is equivalent to 3 mod 5, because 13 minus 3 is equal to 10. And we know that 5 divides into 10. So 13 is equivalent to 3 mod 5, because 13 minus 3 is 10, and 5 divides into 10. Now we want to see if some equivalences are true or not. So we want to decide first, is 12 equivalent to negative 3 mod 5? So remember, what we want to ask ourselves is, does 5 divide 12 minus negative 3? Well, 12 minus negative 3 is 15, and yeah, 5 divides 15, so that equivalence is true. If we look at the next one, is 9 equivalent to 2 mod 7? Well, that means is 19 equivalent to 2 mod 7? Well, that's really asking us, does 7 divide into 19 minus 2? And 19 minus 2 is 17, and 7 doesn't divide into 17, so that equivalence is false. So 12 is equivalent to negative 3 mod 5, and we talked about why, and 19 is not equivalent to 2 mod 7, and we talked about why. So next, I'm going to present the theorem that really does show why the modular equivalence that we just talked about, how that's related to the division algorithm that we talked about first. So it says A is equivalent to B mod n if and only if A and B have the same remainder when we divide them by n. And I'm going to go through the proof with you, but this is sort of a different kind of proof than the sorts of proofs that we've talked about before. So every proof that we've talked about in class before has really been to illustrate a proof technique. So it's been a proof that you should have been able to recreate yourself that illustrates how to use a certain technique of proof. This is a theorem that's important for its own right. It's not important because we're illustrating proof techniques. It's important because in the future we're going to want to know that A being equivalent to B mod n means exactly the same thing as A and B having the same remainder when we divide them by n. There'll be another way to check. We could use the definition, or we could just see, do A and B have the same remainder when we divide them by n? If the answer is yes, then they're equivalent. If the answer is no, then they're not, because of this if and only if statement. So with that being said, when I go through the proof, I'd like you to follow the proof. I hope that the proof makes sense to you. You need to make the proof make sense to you, but you don't need to think while I'm writing it, I would not have created this proof, because this isn't one I would ask you to recreate. I'm proving it because we want to know that it's true, so that we can use it later on. And it'll be a good illustration of how the proof techniques can be used in sort of a more complicated theorem. So let's first prove the reverse direction because it's actually a little easier. So we'll do it directly. So we're going to suppose that A and B have the same remainder when we divide them by n. And then we want to say what that means. So we're going to use the division algorithm. So what that means is then A is equal to nq1 plus r, and B is equal to nq2 plus r for some quotients q, so for some integers q1 and q2, and some remainder r. So r has to be between 0 and n, right? It could be 0, but it has to be less than n. And notice that I used the same letter for the first remainder as I did for the second. A's remainder is the same as B's remainder because we had supposed that A and B have the same remainder. So I chose the same letter for A's remainder and B's remainder, but I had to choose different letters for the quotients because they don't necessarily have the same quotient. They just have the same remainder. So now I know my given and I know what that means. I want to concentrate on what I need to prove. So what do I want to prove? Well, I want to prove that A is equivalent to B mod n. And by definition, that means that n divides into A minus B. So I need to take a look at A minus B and see what it is. And that's going to be just nq1 minus q2. And that means that n divides into A minus B because we've written A minus B as n times some integer. So I'm done. I just have to conclude. Therefore, A is equivalent to B mod n because we just showed that n divided into A minus B, and that's the definition of being equivalent mod n. So then the reverse direction's finished. We suppose that A and B had the same remainder when we divided by n, and we concluded that A was equivalent to B mod n. So now we're going to prove the original direction. It looks like I wrote my arrow in the wrong direction, sorry. So what we want to do is we're going to suppose the given information. So we're going to suppose that A is equal to B mod n, and then write down what that means. So then n divides A minus B, and what that means, so that A minus B is some multiple of n, so for some integer q. And then what we want to prove is that if A and B have the same remainder when we divide them by n. So we want to think about the remainder of A and B when we divide them by n. So we're going to apply the division algorithm to both A and B. So by the division algorithm, we know that A is equal to nq1 plus r1, and B is equal to nq2 plus r2 for some integers q1 and q2 and r's that are non-negative and less than n. So we just applied the division algorithm to both A and B. And remember, we had to use different remainders right now because we're trying to show that they're the same. So we can't assume that they're the same. So I had to use an R1 and an R2 this time. Let's think about A minus B. A minus B, if we substitute for what we know from A and B, that's going to tell us that A minus B is n times q1 minus r1 minus n times q2 minus r2. And then if we just simplify, we get n times q1 minus q2 plus r1 minus r2. So that's what A minus B is. And the reason I thought to look at A minus B is I already know something about A minus B. I know that he's a multiple of n. He's n times q. So if I substitute that, so we already know that A minus B is n times q. So then we substitute and we get n times q is some multiple of n plus r1 minus r2. And then we can rearrange, and we get r1 minus r2 is some multiple of n. And we're trying to prove that r1 is equal to r2, and so it makes sense to consider r1 minus r2, right? Because r1 minus r2 would need to be equal to 0 if r1 is going to be equal to r2. So let's think about where we are now. So we know that 0 is less than r1 and r2 are less than n, because they're both remainders from when we divide by n. So if it happened to be that r2 was smaller than r1, then that would mean that 0 would be less than r1 minus r2, and that's definitely going to be less than n, because they were both smaller than n. So we just subtracted r2 from both sides. 0 would be smaller than r1 minus r2, which is less than n. But that's impossible, because we already know that r1 minus r2 is an integer multiple of n. We just showed that above. He's n times q minus q1 plus q2. But if he's going to be an integer multiple of n, he can't be positive but less than n. We're going to make the same exact argument for the other way around. If r1 is less than r2, then because that would mean that 0 is less than r2 minus r1, which is less than n. But again, we know that n times q, we know that r1 minus r2 is n times some integer. In this case, it's negative q1 plus negative q plus q1 minus q2. So we already know that r2 minus r1 is n times an integer. So r2 minus r1 is an integer multiple of n. So he can't be positive but less than n. He's an integer multiple of n. So since r1 can't be less than r2 and r2 can't be less than r1, it must be the case that r2 and r1 are the same, which was our goal. So therefore, A and B have the same remainder when we divide them by n. So you might want to pause the video and just look at the proof again to make sure that it makes sense to you. But just remember, right, this is a different kind of theorem. I want you to follow the proof, but I don't really want you to be able to reconstruct the proof. It's more important that you can follow the proof, that the proof makes sense to you, and that you know the theorem, that you really remember now that A being equivalent to B mod n means two things. It means that n divides A minus B, that's its definition, but that's equivalent to meaning that A and B have the same remainder when we divide them by n. So in this video, we discussed the division algorithm, which is a way of sort of formalizing the division that you've been doing for a long time, that if we divide A by B, we can write A as B times Q plus R, where R is a remainder, so he has to be non-negative, greater than or equal to 0, and smaller than what we divided by. So, and we discussed kind of if A was negative, then to guarantee that R is positive, we have to overshoot, become more negative than A with B times Q, so that then we can add back something positive to get to where we want to be. And then we introduced the meaning of the statement A is equivalent to B mod n, and by definition, that meant that n divided A minus B. And then we saw that that was equivalent to saying that A and B have the same remainder when we divide them by n.